Hello there, my name is Georgi, and I'm going to give a quick overview of my level 4 project as well as give a demo. So first, the purpose of my project was to build a distributed job scheduler which is capable of being deployed and used at large scale. So let's give a definition of what a job scheduler is first. A job scheduler is an application that triggers the execution of background tasks or background jobs, possibly periodically. A background task is a unit of work that runs independently from the main logic of a given application. And it's best to give an example to illustrate this concept. Many e-commerce platforms provide its users with the ability to be sent daily sales report. The user basically chooses the time at which they want to receive the report, and it is then the system's responsibility to generate the report and make it available to the particular user in a timely manner. Right, so now I will explain what is the problem that I'm actually trying to solve. At an industrial placement I did last year, I noticed that multiple teams make use of a job scheduler in a certain part of their workflow. However, a big part of them had their own proprietary, if you want, job scheduler, which they had to maintain. So this got me thinking, actually, would it not be possible to have a single such system deployed throughout a given organization, which can be used by everyone? In other words, would it not be possible to have a job scheduler as a service? And what would the benefits of this be actually? Let's discuss this. Teams can now focus on developing their applications as opposed to building and maintaining a system that is used so commonly. So I'm going to go straight into the architecture of the system I built, and I will try to be giving justifications of the different components as I'm going along. Right. Scheduling is achieved through message passing. The entities that trigger task executions are a set of replicated scheduler instances. When a task is due, that is, it has to be executed, a scheduler replica sends a message describing the task over to the message bus to either one or more executor components that listen on the other side of the bus. Those executor components will then pick apart the message associated with the task and perform the application logic. So we should notice here that in this way, task triggering, in other words, what the scheduler replica does, is decoupled from task execution. This is what the executors are responsible for doing, right? So far, so good. Why are there multiple scheduler replicas instead of just one? Right, suppose you have X messages, and suppose also that those need to be sent over to the executors all at once. N replicas will be able to achieve this faster than a single scheduler instance. And this is basically the idea behind why we have multiple replicas. Remember, we have multiple teams that would use the system, and we want them to be able to handle, and we want the system to be able to handle a big load. That is many tasks being executed all at the same time. Now, the identity discovery component is used, as the name suggests, to provide each of the replicas with a unique identifier. And this is used so that each replica can access a disjoint portion of all tasks in the system. In other words, we don't want the scheduler instances to be fighting for tasks, as there would be no true parallelism in the system then. The database is for storing task specifications, and this way the schedulers can be stateless processes, which is extremely important for fault tolerance in the system, which we're going to discuss a bit later. And finally, the system API is the component through which users interact with the system. In other words, submit tasks, view tasks, update tasks, and so on. It provides the mechanisms through which users are isolated from one another. In other words, authentication and authorization mechanisms. So the scheduler instances or the scheduler replicas are deployed inside a Docker Swarm, running on a set of AWS EC2 instances. Docker Swarm is a container orchestrator, and it is used to automate deployment of application stacks on a cluster of machines. In addition, Docker Swarm provides fault tolerance mechanisms, and what this means in the context of the system is that if any of the nodes where a scheduler replica runs crashes, like this, the dead scheduler will be revived on another machine and the whole system would continue functioning as if nothing had happened, like this. And this is basically possible because, as I mentioned earlier, the scheduler replicas are stateless processes. Once again, because we have a database, a scheduler replica is free from the responsibility of maintaining state persistently, which is in fact a desirable property in building microservices. It is time for the demo now. Its purpose will be to show the system at runtime. In particular, we will submit a couple of tasks into the system and see that the scheduler replicas are actually triggering their execution. In the end, we will show fault tolerance in the system, that the node crash would not prevent the system from running properly. Without further ado, this user interface shows us the system deployed on a cluster of AWS EC2 nodes, and it also shows us how the different services participating in the system are allocated on the nodes. So the number of scheduler replicas in this deployment is 2, and they are deployed on these 2 nodes here. Here I have a consumer of scheduler messages that will listen from the message bus, and when a message arrives, it will simply print the payload to the standard output. Now, to submit a task to the system, we need to send an HTTP request to the system API because it is built according to the RESTful paradigm. And let's do that. Okay, so what I have here is Insomnia, a REST client, and now I'm about to submit a task to the system. This is the task payload. It would usually be a JSON string and it would encode the task metadata. However, here, for simplicity, the payload is just periodic task 1. Also, this section right here says that the task is to be run every 5 seconds. And this means that every 5 seconds, the replica responsible for the task will send the task's payload onto the message bus, which will then deliver it to our consumer. So let's submit the task. And let's observe if the consumer has started receiving the payloads. Yes, this should happen approximately every 5 seconds, as is the case. Let's go back to Insomnia and let's submit another task. The only difference here is going to be that the task payload is going to be 2. The recurrence information remains every 5 seconds, so the task will be delivered every 5 seconds. Submitting the task is successful, and let's observe if the consumer begins printing the messages, which is what happens here. Okay, so now I'm going to restart a machine where one of the scheduler replica runs. So this replica runs in a machine with IP ending in 12. So let's restart this one. It is this machine. Okay, let's go back to the Swarm visualizer. And let's see what's going to happen. It's going to take some time, of course. Okay, so Docker Swarm noticed that the node is down, and it rescheduled the replica to run on this node right here. And let's see what happens to the messages. So for some time, task 1 didn't get sent, and this was because obviously nobody was there to trigger the task. However, once the replica came back to life, messages started being delivered again, and this is basically fault tolerance in the system. And yes, this is why we needed stateless scheduler replicas. And this is the end of the demo. Thank you very much for your attention. Hopefully you have a better understanding now of my level 4 project. Goodbye.